Thank you very much. It's a deep honor and privilege to be here with you today and to be the follow-on after Michael Morgan, who no doubt gave you a tremendous lecture last year. I'm going to take on a topic that is not a topic I spend a lot of time doing research on, but one that fascinates me very much. And this is my outline. I'm going to tell you what I am not. Jim told you what I am, but what I am not is sometimes as important. I'm going to tell you a couple of things climate change is not. It's a very loaded topic with tremendous amount of emotion associated with it, but there are certain things it is not. Being a physicist, and I know many of you are, invariably it comes down to conservation of mass, momentum, and energy, and we're not so worried about momentum as far as the Earth is concerned. So I'm going to talk a bit about energy conservation, and since I do spend a lot of time in Washington these days, I'm going to couch it in terms of balanced budgets and deficit spending on the part of the planet. I'll then say a little bit about why a little bit of carbon dioxide and methane goes a long way, talk a bit about incoming and outgoing radiation, and then spend a little time on something that I think is a great source of confusion in the community and also in the media, which is the natural and at times unnatural variability of the Earth system. Finally, near the end, for a little bit of levity, if you're still with me at the end of the hour, I will show you some forays into lies, damn lies, and statistics. And finally, we'll talk a little bit about what to look forward to as we proceed to think about balanced budgets. So, a little bit about who I am not. I am not a climate scientist. Never have been and probably never will be. I'm a mathematical physicist by training who, as Jim said, got interested in administration of science. I'm the president of the University Corporation for Atmospheric Research. It's a not-for-profit organization that was created in 1960 by 14 universities across the United States to, at that time, operate the National Center for Atmospheric Research. NCAR is the largest, oldest, most well-known, and the broadest of the National Science Foundation's federally funded research and development centers. And UCAR has had the privilege of operating NCAR since its inception in 1960. But UCAR is much more than just NCAR, which is up in that corner. We're about our 104 university members and affiliates. And earlier today, before this talk, I had the opportunity to spend time meeting many of the faculty and students, some of the deans and some of the vice presidents for research here at the university. You are the 30th university that I have managed to get to visit of my 104 in the 2 years that I've been on the job. And I enjoy every day, and I always say to the last one I'm at, this is the best school I've visited so far. In addition, UCAR has a set of community programs that are very service-oriented activities, things that take the science that's being created at NCAR and our member universities and looks for ways to make that science usable to the citizen who has supported that research through their tax dollars and their appreciation for what we do. Together, this makes UCAR. And so that's what I am, but what I am not is a climate scientist. And so I think you'll find, hopefully, that this is a slightly different version on a topic that you've probably seen many talks. So being a mathematician, let's put it in a formula. As Mark Twain said, climate is what we expect and weather is what we get. And so that's what this equation, my attempt is climate is an average of weather over some period of time. And notice that it depends on two variables. The time t, little t, at which we are making an observation or a measurement of climate, but also ta, the amount of time we do an average over. And we could probably make an even much more complex function by putting a weighting function in there that somehow weighted it towards the present or the past or whatever you want to do. So when we talk about climate, we think about the present climate, but climate being an average of something, and that something also has a lot of variability. Often we speak about temperature, but that's not the only aspect of climate that's out there. Precipitation, humidity, pressure, the list goes on. And the amount of time we implicitly average over also somehow fits into that definition of climate. So if I were to ask you, Over the last 4.5 billion years, if that's my average, has climate changed? Your answer would be I have to wait another 2 to find out. We have one value for what it is. And if I were to average climate and call it an average over a month, then there'd be tremendous seasonal variations to climate that we have known for ages: autumn, spring, summer, fall, but not a particularly useful concept. So in part, when we think about climate change, each of us implicitly has in our mind some time scale that we are doing this averaging over. And that difference in time scales often leads to, I think, a lot of problems. So being a mathematician, of course, I can differentiate this equation, and I hope I've done it right from my elementary calculus. And you'll notice that what I have on the left-hand side is climate change. ddt of climate being 1 over this tau times the difference of 2 weathers at the end point of the integral. And this is probably not a very good definition of climate change. So let's try something different. Let's think about energy budgets. Our Earth is here in space. It is illuminated by the sun each and every day, and it radiates back out into space. And so if we were to write down an energy budget for the Earth, it would look something like this: that there's an amount of absorbed sunlight that comes in so many watts, the amount of emitted radiation that the planet sends back out into space, and if there's any difference between those two, then the planet either is taking up energy or getting rid of that energy in some way, shape, or form. It is either heating, in quotes, or it's cooling, in quotes. Now, what makes this a very difficult equation is the fact that it's highly variable in time. All of these terms are highly variable in time. Let's take the absorbed sunlight. The sun itself has variability in the intrinsic amount of energy it's putting out. The sun-Earth distance changes, and as we move farther away from the sun, the amount of energy falling per unit area goes down because of the 1 over r squared effect. Therefore, even the solid angle that's subtended by the Earth, the net amount of energy coming in varies with position. And then the Earth can reflect some of that back out into space and not bother to absorb it at all. And all of these are complicated, though in some cases knowable, functions of time. By the same token, the emitted radiation that comes off the planet also has variability. And so the classic calculation that you do in all of your courses is, what is the temperature of the moon? If you simply balance the amount of energy that has to come off from a black body, given the basic brightness of the sun at 1 AU, you discover that the average temperature of our planet should be about 255 Kelvin, which is more or less what the moon looks like on average. But because of atmospheric composition, cloud cover, aerosols, and a variety of processes that go on in our atmosphere that are intrinsically interested in itself, for us, this average temperature is actually about 33 Kelvin more, roughly about 59 degrees. So that shows you that this term indeed has a number of interesting things going on. So we might look at this equation and say, well, if absorption and emission balance, then there's no net heating. So is the net heating climate change? If there's a net absorption of energy by the planet or a net loss of energy by the planet, is that how we should define climate change? And I'd argue that it's probably sufficient for climate change if we are in average absorbing or losing energy, but it may not be necessary. There's interesting variability within our system that can lead to climate change even if this equation is balanced out. So let's look at the balanced situation. Here is a beautiful picture from space. You can make out Australia here on the side and New Zealand if your vision is good. And this is what the Earth looks like in the visible light at 0.5 micron. And this is what our planet looks like at 10 microns. And this is the emitted radiation in watts per meter squared. So the first thing you can see is we're actually a little bit brighter in the visible because of the reflected light than we are in the infrared. And notice this cloud structure here. Here's a big cloud area. The cloud is very, very dim in emitted long-wave radiation, whereas it's quite bright in reflected long-wave radiation. And that's because this cloud top is up high in the atmosphere, and the temperature decreases with height in the atmosphere. And so as it radiates back into space, it's radiating in the infrared with a characteristic temperature that is lower than the hot desert ground in Australia at that time. And therefore, Australia appears brighter. So the sun is the planet is interesting in the sense that it's bright at the wavelengths, the long wavelengths it's emitting, and the short wavelengths at which it is reflecting. The reason we're up at 288 instead of down at 255 concerns this plot here, which shows the amount of transparency, if you will, in the atmosphere as a function of wavelength from the visible here at about half a micron out to 10 microns where we showed that last picture. And what the above plot is doing is showing you spread out over the spectrum that reflected albedo, so to speak, and what we're sending out in long wavelength radiation. And you can see that this is our window right here. This is where we can push out that long wave radiation. And if we do anything to clog up that window, if we throw things in that window that prevent the escape or cause the height in the atmosphere where we're doing the emission to move up, because of the fact that the temperature of the atmosphere decreases with height, if we move that emitting height up, it's going to be at a lower temperature and it's going to emit less radiation, and it will put us out of balance. So you can see carbon dioxide here has an absorption band that comes into the side. You can see oxygen and ozone in the middle, methane and nitrous oxide down here. And of course, water vapor, as people will tell you on the news, and from time to time I will come and give you some short news blips that are often out there that are interesting but have no bearing on the problem. Water vapor is our biggest greenhouse gas. So why should we worry about carbon dioxide and things like that? Well, the reason kind of comes from a little bit of chemistry here. What I've put is the freezing points and the boiling points of water, carbon dioxide, O2, I didn't put ozone in, I didn't have room, methane, nitrous oxide. And remember, the average temperature of the planet is about 288. So this one's interesting because it has all of its phase changes occurring in a range of temperatures the planet experiences, where all of these are always just gases, right? These things, unless you're down in Antarctica and Vostok on a very cold day, this stuff is not precipitating out of the atmosphere on you. And so this is a self-regulating process, as we discovered yesterday. Those of you who had trick-or-treaters you had to go with realized the atmosphere was shedding H2O yesterday. As we change these concentrations, a little bit of carbon dioxide, a little bit of methane, a little bit of nitrous oxide can make a big difference because they push that height up where we do the emission from. If we push the height up, we send less energy back into space at long wavelengths. The only way we retrieve a balance is to get that layer warmer to where it was before, and that means increasing the temperature all the way down. So this is an amazing chart that my colleagues Jeff Keel and Kevin Trenberth have put together. And I'm just overwhelmed that anyone can sit down and do this. This is a time average of the energy budget for what's going on in a situation where, on average, over some sufficiently long period of time, the amount of absorbed and emitted radiation balances out. The incoming radiation is 342 watts per meter squared. It could be plus or minus a bit. This is a very hard calculation to do, obviously. And you can see all the different channels. Some is reflected off the clouds, some is absorbed, et cetera, et cetera. And here's the long wavelength going out. And you can see that 342 is equal to 235 plus 107. So we have a balanced situation in which energy is rumbling around in this system, and doing really interesting things in this system. But on the whole, the amount coming in is the amount going out. And this is a balanced budget, and this is something that presumably, on average, the planet likes to relax to given enough time and enough stability in the things that are going on around it, which includes both the inside and the outside. So what I'll do is take a little time to talk about the variability in each of these terms, because often the media will tell you, well, it's the sun. The sun is obviously changing the amount of energy it puts out in time, and we need to account for that, and that changing energy can be driving our climate system. Yes, but no cigar. So let's look at it. The sun sits right here on an astronomical diagram, which I couldn't help to put in, which shows that the sun is one of many different types of stars, and some of the stars you can go out and see at night are up here, and we have their size by how big they are. We have their color, their effective temperature. The sun is about 5,000 Kelvin. That means it emits at about half a micron. Stars like Sirius, the dog star that you can see at night, actually has a temperature of 10,000, so it's emitting farther to the ultraviolet side. And other stars here that are older and smaller and dimmer will emit at lower temperatures. And our sun is what's called a main sequence star. And we actually know a lot about stars because of how we look at their energy production, gain, and loss process. So the next plot shows you, and note the scale here, age billions of years. Okay, so this is nothing to trifle with this scale. Here is the amount of energy coming out of the sun, the luminosity, as a function of time. Here we are now. Here's in the past. The sun was dimmer by quite a bit. The sun will get quite a bit brighter as we go into the future. And the amount of energy the sun is putting out is about 3.9 times 10 to the 26 watts right now. So the sun is changing its luminosity, but to make a sensible change, you would have to wait on the order of 500 million years. This is probably not part of the hockey stick. Right? This is way off in the future, but our star will probably do this. So there are variations in the solar luminosity that come from just the structural aging of the star, the fact that it's burning hydrogen to make helium in its core, and as time goes by, it's converting hydrogen to helium and changing its structure. But interestingly enough, our sun does things on much shorter time scales as well, and that involves the so-called solar cycle. So what I'm showing you here is the number of sunspots. That's what these dots are. Monthly values of the number of sunspots starting, someplace here as we moved up to solar max, 2012-ish or so. And going all the way back to about the 1750s, the very first observations of sunspots were made in 1600 by Galileo when he had a telescope. But you actually don't need a telescope to see sunspots. Some of the bigger sunspots are visible to the naked eye. Disclaimer, never look at the sun with your naked eye, but put a filter in front of it, or as many of the Chinese did way back 2,000–3,000 years ago, when that sun is setting through a lot of dust and haze on the horizon, you can actually see those spots. The number of spots waxes and wanes in a cyclic behavior that is a reasonable clock, but not a very good one, in that some cycles are very long, some are very short, some are strong, some are weak. This variability, we know now that we're out in space, manifests itself in how the sun looks in different short wavelengths. These are ultraviolet wavelengths. And we see 1996 coming around here to 2006. That is taking this period from 1996 around to 2006, that the sun shows activity variation with its sunspot cycle. Why the sun chooses to vary its activity on about an 11 to 12-year time scale is something that keeps solar physicists and solar terrestrial physicists busy to this day. It's a very complex problem, and one whose solution is really not known. What probably is known, that it's a combination of the rotation of the star. The sun rotates about once in a month. The convection, the outer 30% of the sun is convecting, and the strong magnetic fields. The combination of those three effects tends to produce weather, so to speak, on the sun. Now back here at some point, Charles Greeley Abbott, who is the secretary of the Smithsonian, made the great leap of faith that along with this change in sunspot number must come a change in the brightness of this star. He spent literally 50 years of his life going to very odd places in the desert to get up above as much garbage in the atmosphere as he could, to measure the variations in the solar constant. So you can imagine how his grant funding would have gone. I'm going to measure changes in the solar constant. Right, it's a constant. He saw lots of changes. And he took those changes and correlated them against all sorts of things. And in the end, the basic outcome was that all he measured was the turbidity of the atmosphere, that the fluctuations in the atmosphere were so large compared to what the sun was doing that he could not possibly have measured changes in the solar constant. But he was right. Once we could get up above that atmosphere with all of its fluctuations, we could actually measure the brightness, the irradiance, what we see at Earth from space. And here is this solar cycle that we saw before, kind of played out. And on this scale is the irradiance in watts per meter squared. And don't be fooled by the scale. This is 1364. 0 is in the basement, someplace way down in this building. Okay, so this looks like a lot. This is not a lot. This is a small change. And what we have here is a 31-day running mean and also a 365-day running mean. And if we were to do a daily running average along here, these things would become even much larger. So on a short-term basis, there is tremendous variation in the irradiance that comes from the sun, almost at the level of 1%, due to the crossing of sunspots across the disk of that sun. Sunspots, as pictured up there in white light, are dark compared to the disk because their temperature is depressed relative to the surface. They're still a whopping 3,000 to 4,000 degrees Kelvin, which is bright, but they are not as bright as the 5,500 Kelvin of the surrounding areas. So as they come across the center of the disk and block the brightness, they lead to a decrease in the visibility, the amount of energy per unit area coming to the Earth. However, you've noticed that there appear to be wings on each side of that time series. The wings come about because the area around the sunspot, a larger area, we now know to be slightly brighter than the background surroundings. This area has a lovely French name called plage, which is beach. And the brightness of the wings shows up very clearly when it's on the limb. And then when it's toward the center, it decreases and moves back off. So the combination is to make something at first looks bright as you see the limb come into view, dim as the sunspot crosses the disk, bright again as the sunspot exits and back to normal. And basically, the depth of this curve is more or less canceled to leading order by the wings that sit on the side. So even though one event has tremendous changes, and someone will say, wow, the radiation from the sun varies by 1%, that is huge. True statement, but it does it in a sense that it's plus and minus 1%, and it largely cancels out over 2 weeks, which is the transit time of that sunspot. So that in a sense, the net variation here is about 2 parts in 1,300, which works out to be 0.1%. So yes, there's variation in absorbed sunlight on much more interesting time scales, but that's generally not enough to make a huge difference. So what I've done here is shown the difference between the maximum and minimum values of the irradiance as a function of wavelength from about half a micron here. And you'll see that in the visible, our variation along the solar cycle between solar max and solar min is the 0.1%. As you go into the short wavelengths, there's tremendous variability. And recall that picture with how the sun looked so different as we went around those rings between min and max. That's showing that huge variability at short wavelengths. But unfortunately, there's actually very little energy sitting at these short wavelengths. So someone will tell you the short wavelength radiation of the sun varies by 100. It's true, it does. But in terms of the energy budget, this is not an important term. Let's look at one of the other terms. This one is fairly well understood. The Earth lives in an elliptical orbit. Therefore, the sun is at one foci. There's a perihelion where it's closest to the sun and aphelion where it's farthest away. And of course, our axis is tilted about 23 degrees. That leads to our seasons as the planet goes around. And therefore, obviously, when the planet is here, it's subtending and getting more radiation from the sun than when it's over here. So there is an effect of the orbit, which largely cancels out. It's a fairly large effect as far as things go, because we can go back, predict, and measure these variations. So across here is the eccentricity of the Earth's orbit between 0 and 0.05. You are here. It's in one of the times when it has a fairly low eccentricity, but can actually have an eccentricity of 0.05, which leads to very interesting changes in the amount of energy that's coming into the planet at those times. At the same time, the tilt of the axis wobbles from a little under 23 to almost 25 degrees, changing the pronouncement of the seasons. And this is all due to very well-known Newtonian mechanics. It's just gravity at work. And then finally, the perihelion precesses right here. And the combination of the perihelion precessing and also the change in the eccentricity then leads to a pattern like this. And interestingly enough, if you go back, these kind of bumps seem to line up with glacial periods. This axis now going from 0 back to 800,000 years ago. So again, interesting variations in the amount of energy that's coming into the planet because of its orbit, but probably not on decadal timescales. Let's have even more fun. Our sun actually orbits around the center of the galaxy. Here is where our sun was back 500 million years ago. It takes it 250 million years to do one complete orbit around the galaxy. And this is its path shown relative to the frame of the spiral arms. The spiral arms are also rotating with time. From this, you can see that the solar system bobs up and down out of the ecliptic plane. That's what that's showing you. This one is just showing you this constant rotational angle in the middle. And the one up on top is showing you the radius. So it has a very interesting orbit. And when it goes through these spiral arms, people have felt that there are extinctions in some of these interesting periods that could be related to passage through spiral arms. Interesting stuff to look at. Again, none of this very likely to have much of an effect on the sorts of timescales that we're interested here. But yes, the sun does go through the galaxy and do interesting things. Let's look at the emitted radiation part of this equation and the atmospheric composition. If you remember no plot from this talk, this is the one you should remember. This is a solid measurement that's been made out at Mauna Loa. It's been made since 1960, and what it shows you is the concentration of CO2 with a seasonal variation between summer and winter. And you can see that it is not increasing linearly with time. It is doing something different. It is increasing faster than linearly with time. And remember, carbon dioxide is one of those gases that sits on the edge of that window of transparency. So as we throw more carbon dioxide into the atmosphere, and as that carbon dioxide is not raining out, because it doesn't have temperatures anywhere near the temperatures that are going on, we are building up more and more opacity, so to speak. Given the linear trend that we saw from about 1975 to about 2005, we would have expected to get to 400 parts per million in 2025. We passed it this summer. So we are ahead of schedule. Where is that coming from? It's basically coming from us. This is a plot of energy usage. E is an exa, so those are exajoules. The best guess of what we in the United States use per year is about 94 exajoules of energy. And this shows the global consumption going back to about 1800, biomass, hydro, nuclear, and then all of these guys up here are basically fuels that are emitting carbon dioxide into that atmosphere. So one question is that curve going up for other reasons than us? We can use carbon-13 to carbon-14 ratios and various other things to more or less unequivocally be able to ascertain that this is the cause of that rise that we are seeing from about 1960 going onward. So it is us. And what is it doing? Putting this chart back up. It's pushing in and fitting this gap. Here is the amount of carbon dioxide in the atmosphere from 2005 back to 20,000 years ago. How on earth do we know the carbon dioxide 20,000 years ago? Air bubbles trapped in cores from glaciers. Wonderful stuff. We can actually go back even farther in time, and you can see that even if we were worried about natural variability in this system, suppose the carbon is just going up for natural reasons, it's a natural variability we have not seen in 20,000 years, if it's a natural variability. And we didn't get to the 400, right? It's off the top of the page. And so that's what we're seeing with carbon dioxide. Question for all of you in the audience, extra credit question. When was the last time on this planet that the concentration of carbon dioxide was 400 parts per million? 100,000 years ago? 500,000 years ago? 2 million years ago? 2 million, yes, probably around 2 million years ago. We cannot in an ice core find a parts per million at 400. So we're doing something interesting to this planet, albeit we've had some help. Natural variability got us up to around 280, so we had a good starting point, but we've really gone to town with that. What we see with carbon dioxide is the same as what we see with many of these other trace compounds. Here's methane. That's what the methane curve looks like. Ouch. If it's natural variability, it's again affecting the methane. And nitrous oxide, also doing similar things. So we are changing our atmosphere. What does that do to our energy balance? So Kevin and his colleagues went back, sharpened their pencils, redid the numbers, added some more significant digits, and what you see now is that the outgoing radiation is not matching the incoming and reflected, and there's a deficit of about 1 watt per meter squared. So we are deficit spending. Because of our elevated levels of those sorts of gases, on average, we are seeing the planet absorbing about this amount of energy. And what does that work out to per year? 10 to the 22 joules is about how much that works out to. And we'll see how that stacks up. So this is the net effect. Our energy is not in balance at the moment, and it continues to stay out of balance. The natural variability, of course, clouds the whole issue because people want to look for what that impact is. We have a surplus of shortwave visible light showing up at the equator relative to the poles, but the poles tend to radiate more at the long wavelengths than the equator does. So this leads to an energy transport problem, which as the world turns, my mom loved watching this as a kid, leads to all these changes. This is weather. This is why life on the planet is so interesting, is that unequal heating coupled with the rotation of the planet creates all kinds of variability. Here is one index that meteorologists use to define that variability. It relates to things happening in the North Atlantic. And you can see lots of healthy variability. I don't know. I don't see a trend there. Maybe some of you see a trend there. So I'd call that natural variability, which can often be used by people to say, well, look, this is the most negative value I've ever seen, so it must be the case that climate is not warming because there's a negative value. Here's another great example of natural variability, which is the El Nino La Nina effect. It's important because it regulates the way in which the ocean can share energy with the atmosphere. There are times when the ocean is warmer, and therefore it's putting more energy into the atmosphere. There's time where it's cooler and it's taking it out of it. So there's a constant sloshing back and forth between energy content of the atmosphere and the ocean. Here's another piece of unnatural variability. This is a really beautiful plot. What we're showing here is kind of a hodograph of the volume of ice in the Arctic, starting in 1979. And as days of the year go by, we start here in January, we go to April, we come to July, October, and then we complete a year. So one circuit around here is 1 year, and the distance from the origin is the volume of ice in the Antarctic. And what do you see? Well, you see that obviously when we're here in the late spring, we've got the biggest amount of ice present. That makes sense. And that as we go into the fall, we have the least amount. But this thing is slowly making its way in towards zero. This looks to me like some unnatural variability compared to the other things we've seen. And here's a picture that more or less illustrates September 2012, what the ice cover is, September 1979. So parts of our system have variability, but other parts seem to have trends sitting upon that variability. And ice mass is one of them. Here's another one. This is an amazing measurement to make. And we can only do it because of geodesy and GPS, having amazing satellites out there that can actually measure the height of the oceans. And what we're seeing is the global sea level change on average from 1992 to 2012. And we are increasing at the level of 3 millimeters per year. There's certainly natural variability in there, but there's also a rather clear trend of something that's happening there. And this is a fun chart that says this is where this coastline is going to be in 2030 and 2050. So again, variability in the system, but we're seeing a trend. A lot of thought goes into extremes, and I want to talk a little bit about extremes. We focus on extremes. The media grabs extremes for a lot of reasons. What I'm showing up in this figure is from a set of stations across the US, and this is the US, so it doesn't mean it's a world thing, so take this with a grain of salt because all climates are not equal, that shows the number of daily maximum record temperatures from these 970 stations, and this comes from John Christie's work at the University of Alabama, starting back in 1895 and going through to 2015. And in the same format, with the same scale, I show you the number of record lows that are observed at those stations. So you can see that there were some horrible things happening in the 20s, 30s, and 40s in terms of lots of variability. I put lines across to show the averages, and here's this current event where the number of lows is decreasing. Now, many people who think climate change is not happening will point to this and say, look at, the number of record highs is not increasing. If climate was changing, the number of record highs should be increasing. Not true. If you had a distribution of records and you picked from that same distribution randomly, it's pretty easy to convince yourself that as time goes by, the number of records you have to get farther and farther apart, because it's rarer and rarer to get beyond that last high number that you got. So if climate were not changing, the number of records per unit time would have to decrease. They're not. They're staying level, at least on the record highs, and they're dropping on the record lows. So one way to look at this is that the distribution is moving towards the hot end, and here is a plot that illustrates from Jim Hansen's work what he calls the anomalies this is June, July, August temperatures from the northern hemisphere, and these are standard deviations away from the average, and these are the anomalies he sees from his sites. And you can see there's a Gaussian we've put there in green, and as we move to different decades, you can see that this Gaussian is kind of sliding off to the high side. So there is a sense here that the extreme events, while no one extreme event has anything to do per se with climate change, the preponderance of extremes and how they line themselves up statistically does connect to changing distribution functions. So let's look at temperature as the last thing. Temperature is often something people use, and I haven't showed a temperature plot. I've left it towards the end. This is an amazing picture. This is the average temperature, annual temperature of the Earth. And thank goodness we have these large areas of ocean that are pretty homogeneous, because I don't know how on earth you would compute an average temperature based on all the variability you see in places like that. I find it interesting that even though the global mean is sitting here around 288, someplace right in here, if you ask what is the coldest temperature we've ever recorded on the planet naturally, it's 161 Kelvin in Vostok in 1983. and the hottest is 329 in California. It's very skewed towards the low end, right? It's very hard to get high temperatures out of this distribution function. Somehow when things start cooling, when carbon dioxide starts precipitating out of the air, it's really easy to cool down. So this is an interesting point that they're fairly unequal. And this is our plot. So global mean temperature is in some sense, again, an average over a certain period of time over the area of the planet, of the temperature, say. And this is the best reconstruction people can make of that from very noisy data, and a lot of effort goes into this. That plot you've seen, I think, over and over again. And so it's compelling to ask yourself the question, is the global mean temperature what marks climate change? And I'd say it's necessary, but perhaps it's not really sufficient for that. If the global mean temperature is moving rapidly in different directions, that could well be a harbinger of climate change, but the climate could be changing without it moving in different directions. In point of fact, let's look at this period here that just came out of the IPCC. A great amount of effort has been expended in the press talking about the hiatus in global warming, the flattening of that curve. Is that telling us that everything we've said before is wrong? I don't think so. I think what it's telling us is there is a lot of natural variability in this system, and that we have to think about one other place where we can put heat, which is the ocean. This is a plot of the energy of the ocean in 10 to the 22 joules, which is 10,000 exajoules, if you're remembering. These are great units, aren't they, exajoules? If you remember the other scale. Here we are, this period from about 1995 to, and you can see what has the ocean been doing? It's been warming up. If you ask in that energy balance equation, 1 watt per meter squared, how much each year we should be adding if we put it all into the ocean, assuming that was correct, and it works out to be about 1 or 1.5 times 10 to the 22 joules per year is what the planet is absorbing on the whole. And so these numbers are not bad. They're more or less in the right order of magnitude for what we want to see. And so this rise in temperature of the ocean, or heat content of the ocean, overlaps very nicely with this period in which the atmosphere has not been increasing its temperature. So there are many places to store energy within our system. So let's have some fun. In the last few minutes, I want to perhaps get some giggles from you all and point out that those are the facts. That's what we know. But there are many ways to take facts and confuse them. And they can start a long time ago. So what I'm going to do is give you the top 10 ways to make a complicated problem, climate change, no doubt a complicated problem, even more confusing than it already is. So here's number one. What I'm showing you here is the sunspot number from 1780 out to 1880. And it has three of our top 10 reasons. Here is the temperature in Paris. Notice how well the Paris temperature follows the sunspot trend. Never mind what the ordinate is. We assume somehow temperature is going to work right here for Paris. And guess what? At this point, where Paris probably diverts tremendously from this curve, we quit plotting. Instead, London. We go over and pick London for a while. And look how well London is doing here. Whoops, Paris comes back because I think London's in trouble. And then we actually go to Eastern Europe. Tomasz, I'm sorry we didn't go as far as we needed south. We stayed in Prague. And now Prague is doing just, great. So, shift and dilate your ordinate. That always helps. Cherry pick your geographical locations around the globe. This has to be the sun doing it, right? Look at how well it lines up. And choose and start your time series where you wish. Rules number 1, 2, and 3. Let's go on to number 4. Use obscure time series. Notice that tropospheric is misspelled, but that probably doesn't make a difference. Here is cosmic ray decrease in percent. And you'll notice the cosmic ray decrease in percent curve is pretty robust, though we do a scaling. And if you look at this one, you say, this is really not a good fit. Nothing is correlating here. And they, in fact, tell you with 2 significant digits. Now, if we use a different radiosonde temperature anomaly, and it's not clear why this one is not as preferable as this one, suddenly, voila, we have a very nice correlation with tropospheric temperature. Cause and effect. This one is a lot of fun. So what we're plotting here from 1900 to 2000 is, of course, the sunspot number again on this side. But this is the lake level of Lake Victoria in Africa. And as you can see, from 1896 to 1928, Lake Victoria knows about the sunspot cycle very, very well. For some reason, we have to put labels in the middle of our graph instead of at the sides, and that means we don't plot any of that data, where there was either no lake or no sunspots. Wait a minute, there were lakes and sunspots, but you know what? Nothing lines up during that period, so we don't want to plot those. And we come back in 1970, and lo and behold, we're in sync again. We're doing pretty well, but we actually have to detrend for the minus 29 millimeters per year falling trend that comes out of it. So omit inconvenient data and always detrend your time series. I know someone here is studying the quasi-biennial oscillation. Sunspots across the bottom, an index of the quasi-biennial oscillation. And I think someone only had data for this period and periodically continued it backward because these plots are exactly the same. There's no variability in this thing. So rule number 7, when you can, periodically extend your time series back in time because you never know what's going to happen. Some good things could happen. This one, I have no idea what to make of this one. Here we have sunspot number again. This is the cumulative, the integral of the ENSO anomaly, and sometimes things work, sometimes they don't. I have no idea what someone was trying to do with that. Is there an issue? And why not just do the full Monty? Missing the issue. Here we have sunspot number against number of Republican senators in the Senate since 1959. Now, the study didn't point it out, but I need to share with you that it's better than this. The number of Democrats anti-correlates very strongly at the same level that the Republicans correlates. And then here, look what happens. We go from sunspot number to scaled and inverted sunspot number. Yow! Maybe that says something from 1988 on about the nature of our people in Congress or not. Here's another one, the Holgate 2007 is an attempt to bring back sea surface before we have really the measurements from space that are precise. So it's a difficult thing against sunspots. And why not differentiate a noisy time series, right? Rate of sea level, not sea level rise, which is probably hard enough, but rate of sea level rise. So flip correlation in midstream, seek additional correlations, and when in doubt, differentiate noisy time series. Those are my top 10 rules from the Home Office in Nebraska as to why we should be wary. Here's a fun thing. I wish I was Philip Mirowski. So he starts the abstract to his paper saying, it may seem odd to disinter an economic theory. In this instant, William Stanley Jevons claims that sunspots caused macroeconomic fluctuations, which no one now believes or much cares about. Footnote, well, almost no one. Compare David Cass and Carl Schell do Sunspots Matter. Jevons felt that sunspots had an impact on financial markets. And he was a strong believer in that. And he even had some ideas that since the sunspots were changing the brightness of the sun, that was changing the yield of corn. And therefore, that was going to cause the markets to go up and down. And what this paper is about is that people actually began believing in the sunspots, in trading in markets. If you believe the sunspots are controlling Wall Street, you will make investments based on projections of the sunspots, and guess what will actually happen? Sunspots will actually begin controlling the market. Not because they actually control the market, mind you, but because people think they control the market. So that's what this gentleman's paper is about, is how things that really don't control markets have a way of controlling markets. So I want to end with this slide. Again, if you take away nothing, it's this plot and this net absorbed amount of energy. And in some sense, if we want to think about how we change our futures, we have to bend this curve. This curve is going up. You've seen pretty clearly what this curve going up does to us. It will take us a long time to adjust to that curve going up. And how, in fact, we adjust that curve is something that I think we need to think about. Don't be fooled by natural variability and all the diverse timescales. Those are all those media reports that come out and point to one event. There will be climate change winners and losers. It is not written anywhere that the current climate in which we live is the best of all possible climates. It may not be. But the problem is we've built and created our lives to fit within this climate. If it's going to be a different climate, we have to take that into account as we change our lives and social structures going forward. Almost anything is possible. Could the sun be emitting things that are really heating up the planet? Yada, yada, yada. Sure, it's possible. Richard Feynman was once asked, is it possible that UFOs are real? He said, absolutely. I would not take that bet in a million years. Right? So things are possible, but it doesn't mean they're probable. And then to poke a little bit of fun at Shakespeare, the problem is probably with us and not with our star. As to where we are now. And finally, Kevin Trenberth's advice to all of us, there's no planet B. My very last picture is to remind us that sometimes things aren't really as hard as we make them out to be. Svante Arrhenius, who won a Nobel Prize at the turn of the century, noted in 1896 that carbon dioxide would build up in the atmosphere due to industry, and he lived in a time with a lot of industry. Calculated that the Earth would warm by 4 degrees C for a doubling of carbon dioxide. Compare that with the most recent IPCC report. And so it's not magic. It's just basic physics, and that's what I am. And I thank you very much for your time this afternoon, and be happy to take any questions. Thank you.